In this video, we're going to study optimization. If I have some particular function that depends on an x and a y, how do I find where this function has a maximum? How do I find where it has a minimum? And sometimes, how do I find where it has this interesting new phenomenon called a saddle? In the single variable case, there were actually three different major possibilities. The first of them was you'd have a minimum, so some point, for example, the function x squared, and it would go up, and at the value of x equal to 0, you would have a minimum. And at that location, the derivative was 0. You had a horizontal tangent line. The function appeared to sort of bottom out and flatten off at that point. Likewise, we had maximums, and also a third case where it appeared that the derivative was 0. You had a horizontal tangent line at the value of x equal to 0. But in this third case, an example of which is something like y equal to x cubed, that it was neither a maximum or a minimum. It went up and it leveled off, and then it went up again. Now, the first thing to say is all three of these scenarios repeat themselves in the multivariable calculus case. You can have a minimum, you can have a maximum, and that neither situation can also occur. You can sort of be going up, flattening off, and then going up again. But there's a new situation that can happen in the multivariable calculus case that couldn't happen before, and that's the idea of a saddle. When I have a saddle, when I look at one of those directions, for example, I've plugged away, if I go along the x-axis, I get this yellow curve, then it appears to be a minimum according to the yellow curve. But if you go parallel now to the y-axis at the point 0, 0, you get this blue curve, which is going downwards, and then it appears to be a maximum. The idea of a saddle is that in one direction it appears to be a maximum, the other appears to be a minimum. When you have both of those properties, you get a saddle. In single variable calculus, it wasn't relevant because you only ever had one direction that you could go. Now, these two curves, the yellow and blue ones, the yellow one is what happens when I just plug in the value of y equal to 0. And if I have a multivariable function, f of x and y, and I plug in y equal to 0, I now have a single variable function, and you can see its graph. Likewise, for the blue one, if I plug in now, this time, x equal to 0, I also get a single variable function, f of 0, y. Because they're single variable functions, I can use all the analysis from first-order calculus. If I wanted to find that something was a minimum, you took the derivative, set it equal to 0, and those gave you candidates to be minimums, maximums, or neither. So in both of these cases, I can take the derivative with respect to x of the yellow curve, or the derivative with respect to y of the blue curve, and both of those are derivatives of single variable functions. Now, one of the big features of single variable calculus was just because the derivative was 0 didn't tell you it was a max or a minimum or neither. You had to do more analysis beyond that. But setting the derivatives equal to 0 gives you candidates to be maximums and candidates to be minimums. And the same exact story is going to be true here. It's just that when I take the derivatives of these yellow and blue curves, the derivatives, say, of f of x comma 0, that is going to turn into a partial derivative in the multivariable case. So this is my statement of the so-called first derivative test. It says, if you have a local max or min at a point, then the following must be true. It must be true that both of the partials are 0 at that particular point. So this is the exact analog of the previous theorem in single variable calculus, saying that if the function had a maximum or minimum point, the derivative had to be 0 at that particular point. Now, let's see an example of this. So I'm going to give the parabola x squared plus y squared. So if I want to go and figure out, well, where is the partial derivatives equal to 0? Where is my candidates to be a maximum or a minimum? Well, you take the first partial derivative, which is 2x, set that 0. It might give you that x is equal to 0. Take the second partial derivative, this is going to be 2y. If I take it with respect to y, set that equal to 0, you get y equal to 0. Just because I tell you that the partials are both 0 doesn't tell you whether it's a maximum or a minimum or neither. We have to investigate a little bit further. But in this particular case, if I just look at what the function is, well, the function is always positive or equal to 0 at this one spot 0, 0. So that one spot 0, 0 we discovered has to be a minimum because the function is always bigger around it. But notice how I'm doing a bit of an ad hoc argument here. I had to go investigate the sort of specifics of the function, you change the function, and this analysis might be harder or smaller. It's easy to find candidates. It's easy to find candidates to be maximums or minimums, set the partials equal to 0. But how do I really know that they're going to be maximums or minimums in a general case where I can't just do this easy little bit of analysis? Well, for that, we have the analog of the second derivative test, and here it is. It's a lot to it, so we have to unpack it. Basically what it says is the following. First of all, assume that your functions are nice. So what I mean by that is that the first and second partial derivatives all are going to exist, and they're going to exist on some open disk around your point. So you've got some nice functions. Then it gives you conditions to tell you whether you've got a max, a min, a saddle, or when the test fails and is inconclusive and you cannot use the test. So the test is not complete. It tells you sometimes you can use this test and sometimes it's inconclusive, but a good number of times we can use the test, so it's worthwhile knowing. Okay, the conditions here are a little bit weird. There's something about the second derivative fxx being negative, being positive, but then there's also this weird expression in pink, the second partial with respect to x times the second partial with respect to y minus the square of the mixed partials fxy, and whether this is greater than 0 or less than, what's going on? So let's try to break it down piece by piece. First, I'm going to study as an example of a minimum here. Now, what I've highlighted in yellow here is the curve when I plug in y equal to 0. So I have f of x 0. Then the second derivative of that curve tells me the concavity of it. If the second derivative is positive, it tells me that this yellow curve is facing up, it's concave up. If the yellow curve here is concave down, the second derivative will be negative. Indeed, we use this analysis of concavity in single variable calculus to tell whether or not our particular point that was a candidate to be a maximum or minimum was a maximum or a minimum. And so, indeed, it makes a lot of sense that we demand that the second partial is going to be positive if this point down at the bottom is going to be a minimum. And likewise, if it's going to be a maximum, you'd expect the exact opposite, that the second partial has to be negative, which means it's concave down. However, studying just the partial with respect to x is not enough. You might think, okay, well, why don't you go and also look at the second partial with respect to y? So if you go the other direction, if you fix your x value, your y is changing, look at the second derivative of that. Is it concave up, concave down? So that is actually done a little bit in the middle of the pink expression. The pink expression is where fyy first appears. But it's a little bit complex. So let's switch to the third scenario that could happen to see why we might have this. Let's look now at the saddle. Well, in the case of the saddle, what we have is that my second partial with respect to x is positive, but my second partial with respect to y is negative. So this means it's sort of concave up in one way, concave down in the other, consistent with my notion of a saddle point. And then if I go and look at what the product of these two things are, the partial of f with respect to x twice and the partial of y with respect to y twice, the product of those things is sort of a code for whether the two partial derivatives have the same sign or an opposite sign. So, for instance, in the case when they have opposite sign, like one is concave up in the one direction and concave down in the other, so positive second derivative in the one direction, negative second derivative in the other, then the product fxx and fyy will be negative. Since we're then subtracting something squared, which is always positive, in the case of a saddle, what you have is that if these mixed partials are opposite directions, for sure it's going to be a saddle. So I think so far we've justified why we have the fxx being less than 0 and greater than 0 when differentiating between maximums and minimums. And we've also seen the sort of first part of my pink expression, the fxx times fyy, why the sign of that might be important for telling us whether or not we have a saddle. But what about the other part of this expression? Consider the following weird example. Okay, so this is a new example, and it is a weird type of saddle. It's actually the function x squared plus y squared minus 3xy. Now, if I go along here and I specify that I'm on the x-axis, so I plug in y equal to 0, then what I just get is the curve x squared, that's what I've highlighted in yellow, and x squared, its second partial derivative, is just 2, which is positive, it's concave up as you go along the x-axis. Alright. But what happens when you go along the y-axis? Well, almost the exact same thing. If you're going along the y-axis of this now, it's also concave up. Indeed, the function is y squared along the y-axis, and its second derivative with respect to y is 2. So whether you go along the x, whether you go along the y, it's concave up in both directions, which might make you think that it should be a minimum. And yet, if I choose this somewhat clever third path, path. What if I go along the path y equal to x now? So I'm here, I'm restricting to y equal to x. And if I plug that in, then what I get out of this is x squared plus x squared minus 3x squared. I get minus x squared. Minus x squared is concave down. So basically, going along the x-axis was concave up. Going along the y-axis was concave up. But going along y equal to x, it was concave down. Now, watch what happens to the mixed partial, the f sub x y. Well, first of all, I'm going to say that that's taking the partial derivative with respect to y of, I take the partial derivative with respect to x, 2x minus 3y. I take that partial, and I get the value of minus 3. When you square that, you're going to get 9, which is just much bigger than the 2 times 2 that you have for fxx times fyy. So in this case, considering that fxy, the so-called mixed partial squared, it allowed us to see that this was a saddle, even though the analysis along x and y respectively could not see that it was a saddle. Indeed, it can be going down in some direction that's not the x and the y axis. So the way I think about the mixed partial is that as I change my x, if for example, the partial derivative with respect to x, partial derivative with respect to y now, as I study that, it changes as I move off of the x-axis. And indeed, you might recall that fxy was equal to fyx, so likewise you can study the partial derivative with respect to y and then see how that changes as you move the x, which is now moving off of the y-axis. So the mixed partials are a way of figuring out what happens when we're not just constrained to the axes. That's what fxx and fyy does. The mixed partials tell us, well, how big are these changes if I go off a little on x and then I go out along y? That captures changes, for example, in y equal to x, which is not along either of the axes. And so if as you change x and then as you change y, which is taking you off the axes, if that change is very large, then the fxy squared is going to be very large, and indeed then you can have a saddle even when along both axes it appears to be a maximum or appears to be a minimum. Now, exactly proving the second derivative test beyond the intuition that I've given you is beyond the scope of this particular video. I can tell you that it comes from the generalization of Taylor's theorem, we've seen in single variable calculus, to the multivariable calculus case. And indeed, we're going to have this expression is related to something called the Hessian, and that will be our way to formally demonstrate that these conditions are valid ways to decide whether something is a maximum or a minimum or a saddle. From the computational perspective, our method is now relatively straightforward. You find all the candidates by the first derivative test. That is, you go along and you figure out where is the partial derivative with respect to x equal to 0, partial derivative with respect to y equal to 0, and when both of those occur, then the second derivative test gives us the conditions to classify those. When is it the case that it's going to be a maximum, a minimum, a saddle, or unfortunately sometimes the test fails and we have to go further, we have to do more analysis than we can get from just this test.